Okay, we're at section 6, which is the last section, and this is called improving test results. We're just going to look at different ways in which the test results could be improved and might be affected by other parameters or other events. So this is the actual physical test process in the model, and you've seen this slide before. We have the priors, PR of I, that's the prevalence, and then we have the whole process of taking the swabs, extracting the viral RNA and then putting it into the machine, and we get either a positive outcome or a negative test result. And that maps into the model below. And from that model, we can work out the 4 posteriori probabilities as well as the test accuracy. So the question is, do we need to improve the test results for the PCR process? Well, in fact, we can see that we actually do, because one of the big problems are false negatives. This is where you tell someone that they don't have the disease, but they actually do, and they go out and infect other people. And what a recently published paper, the reference is given at the bottom of the page, is in that typically 4 days before the onset of symptoms, you can have dangers of really high false negatives, probability of false negatives. So there's the binary channel again. And there's the important equation, the probability that you're infected given that you've tested negative. So that's the equation for the false negatives. And I've highlighted in red the probability of being negative given that you are infected, which is the diagonal going from top left to bottom right. And that's 1 minus the sensitivity. So this is taken from the paper. We have 2 plots here. On the first plot at the top, we're plotting the probability of, as I say, testing negative given that you're infected. And as you can see, before day 5, when the symptoms appear, you've got nearly 100% for the first 3 days, and then 75% for the next 1 or 2 days, which means that the sensitivity is 0 or 0.25, extremely low. You can look at all the practical reasons why that might happen. And then it goes down after about day 6 or 7, and then slowly increases. So we're looking at the first graph, and we're looking at the parameter in red. Now that parameter in red, of course, as we know from everything you've seen, doesn't tell you the probability of a false negative. What tells you the probability of a false negative is the probability, given that you've tested negative, that you're actually infected. And that's the equation in the bottom right-hand corner. But you can see how that red parameter does influence it, but the probability of the false negative is a lot reduced because of the priors that have been assumed here. However, you can see that in the 4 days before symptoms appear, you have 11% probability going down to 5% on day 5. Of experiencing a false negative if you test negative. That means you can go in and test negative and be released. That means 10 out of 100 people who have that experience will actually be infected and will go on to infect others. So that's quite a serious issue. So 2 things there: the probability of false negatives, which unfortunately are high-ish for PCR tests. And secondly, the fact that these false negatives are very high before the symptoms actually appear. So if you're doing testings before the symptoms appear, that's probably the worst time. So let's look at the importance again of priors on false negatives. So from that same paper, what they did here was they looked at the probability that you would be infected given that you tested negative, that's the false negative, and they looked at how that changed in the days since exposure, but parameterized this on the pretest probability. So we know that the priors are very important. And we can see here as the prior is, when the priors are very high, then the probability of a false negative is large. And when the prior is low, the probability of a false negative goes down. And these curves follow exactly the same way as the previous graph, where they're very high on the days before symptoms appear, reach a minimum, and then start increasing again. And you can see why, if you have a high pretest probability, that's the probability of why that should increase the false negatives, because If the probability of I is very large, then you're going to get a greater contribution going on the downward diagonal from top left to bottom right, and that's going to increase the probability of a false negative. So if the pretest probability was 44%, you can see on the early days before symptoms appear, you can have as high as maybe 45% of people who test negative having false negatives. So that's extremely worrying. Okay, so let's look at the first way of actually maybe improving the test result. So we can look at improving how we actually take and transport the actual swab itself. First question is, how much virus is the person shedding? People can shed different amounts of virus at different times, and that can be an issue. The second thing is the swab taken by someone who's experienced, because a nurse will know how to take that swab properly rather than you doing it yourself. So apparently the main nasal swab tests, they examine the nasopharynx, which is where the nose meets the top of the throat, and this is very difficult, I believe, to access properly, and so there could be some portion of false negatives that arise from not doing that properly in the proper way. And the thing, even if it's done properly, the swab might produce a negative, and one of the possible reasons for that is that as the disease progresses, the virus passes down to your lower respiratory system, and so it's not as easy to detect it by taking that swab, and in that case the patient may be asked to cough up some mucus from the lower lungs. And the other issue would be, how long did the swab sit around? Was it looked after properly? How long did it take to transport it to the laboratories themselves? So that's just a list of some of the possible things that could go wrong with the actual taking of the swab and the transporting of the swab, and that will affect the parameters in our test model. Second thing might be improving the actual PCR process itself. So apparently, and I'm quoting a paper at the bottom, there are editing errors that can occur in the PCR process as regards DNA, and errors that can occur to the DNA due to thermal damage. So that's actually within the machine itself in trying to look for the presence of the virus. So another way that you can have errors, or how you could improve on those errors, is to, I said before that you can't really change the disease prevalence. I should really have had another parameter, which is not the disease prevalence, but it's when you present what is the likelihood that you have the disease, and that likelihood can increase by looking at your symptoms. So while PRI does not change the actual test outcome, it will influence the posterior probabilities and the overall test accuracy, which depend on the prevalence of the disease. And you could improve on the estimation of the probability of whether you have the disease or not by mathematical models, or looking at patients' symptoms like age, lifestyle, current health, etc., and so estimate more accurately both the prevalence, or the probability that you have the disease, and the important probability of a false negative given a negative in the test. So I think I used that earlier. So how you actually work that out, I don't know. So if you turn up and you've lost your sense of smell and your sense of taste, and you've got a fever and you've got a dry cough, then the probability that you have COVID, PRR of I, would go up to, I don't know, 0.8, 0.9. What you could do is you could take, next thing you could do is take information from many different sources and fuse it together in some optimal way, or train a machine learning program. So you use the output of the PCR result. You could look at your location, wherever you are, the disease prevalence. Are you near an epicenter? Have you recently come back from some tourist destination? Do you live in a remote place where there's no evidence of the disease? Looking at your travel history, social context. This could be integrated with a digital COV app that's being developed. Look at your health data, your symptoms, and your age and your history. And finally, a sort of gold test would be some sort of imaging, X-ray or CT scan. And if you put that all together and somehow fuse the data in an optimal way, you increase your probability of getting more accurate result, I suspect, than just relying on the PCR test itself. Now, another thing that's often been mooted, well, actually does happen in some countries, is to take the test more than once. So this was a headline in the UK paper, the Daily Mirror, which said on the 16th of April that a UK nurse had 3 negative swabs before confirmation of the disease, with a 4th positive swab and also a CT scan. So in Turkey, I think they ask for 2 negative results before they'll say you don't have the disease. And in some other countries, I believe they require 3 negative results. So I took this as an example. Imagine we are told that the sensitivity of the test is 0.7 and the specificity is 0.95. And James, who presents with fever and loss of taste, how many negative test results must James obtain in a row to reduce the probability of a false negative to below 4%? Let's assume that's the threshold. They say, we're fine to let you go if we know for certain that your negative test, the probability of that being a false negative is 4%. That's low enough for us to let you go. I feel a bit sorry for James here because he seems to be presenting daily with symptoms of COVID. So how do we do the maths for that? It's not totally obvious. You might think that's very simple. It is simple, but you've got to be careful. So the probability of being infected, given that you've got a negative, from all that we've learned, that works out as about 59%, given a prevalence or a probability of having the disease of 0.8, and that's based on his symptoms. So what you could say there is, okay, let's have him test more than once, and we're going to change the nomenclature here. So at the bottom I've said let PRI, a vertical line conditioned on N, large capital N, brackets lowercase n, mean the probability that you're infected given that you have taken N tests and tested negative N times in a row. So let's assume you've tested negative 2 times, 3 times, 4 times in a row. What's the probability that's false negative? Clearly, the more times you test negative, the lower will be your probability of false negative. So if you do the maths, first of all, you have to establish the formula. So you need to use Bayes' theorem here again, and it comes out like this. And the only thing that you have to be careful about is you might think that you actually, the probability, if you look at the denominator on Bayes' theorem, the probability of n, capital N of n, you might think that that's just the probability of n of 1 all raised to the power n, and it's not actually. And if you do that, you can see that after 4 tests, the probability of a false negative is 3.8%. So here I've plotted the number of negative tests, n, against the probability of the false negative. And once you have 4 tests, you're below the 4%, that is the threshold. So 4 negatives would be fine in this particular case, in this imaginary country, where they require you to be below a 3.8% probability, a 4% probability of a false negative. Okay? And here's a little note at the bottom about how easy it is to make a mistake about that denominator and what it actually means if you raise the probability of capital N brackets 1 to the power n, which is incorrect. So what happens now if you get a mixture of positive and negative results in n tests? So you're not necessarily always going to get 4 negatives in a row. What if you get 4 negatives and you have 1 positive in the middle, or you get 6 negatives with 2 positives? So again, you go back and you try to work out the maths for that. And again, it's not difficult, but it's just easy to make a mistake. So I'll leave this for you to look at. So here we're saying you have N1 negative tests and N2 positive tests. And we're going to change the nomenclature again. So we're going to say the probability of I being infected conditioned on Tn1, N2. So Tn1, N2 is you've tested negative N1 times and you've tested positive N2 times. So T is the test, N1 negative and N2 positive. So if you plot that probability, you get this 3-dimensional representation. So you can go along there and you can put in the number of positive tests, the number of negative tests, and you get the probability that you're actually infected. It's much easier to see it like this. So here I take 2 positive tests and I get 4 negative tests. Now it doesn't say how they occur, how you mix up the 4 positive tests and the 2 negative tests. So they could happen anyway. You could have 2 positive tests at the beginning, or test number 1 could be positive and test number 3 could be positive. So in this particular case, the probability after 2 positive tests and 4 negative tests is that you're 88.6% likely to be infected. And you can do the same, by the way, for other, probability that you're not infected, etc. Okay, so the probability of this being like a false positive is 11.4%. Okay, now what we can see again is that the system is much more sensitive to changes in the number of positive tests, N2, than the number of negative tests. And that can be seen in the model that we'll show you in the next page. So if I set the number of negative tests to 4, and I move to the right, increasing the number of positive tests, you can see that it rises very fast going from left to right. But if I set the number of positive tests to 4 and I start increasing the number of negative tests, then it decreases much more slowly. Lastly, if I take a diagonal, what that is saying now is that we're setting the total number of tests to n, in this case 10, and so we keep the total number of tests fixed at 10 and we vary the number of positive and the number of negative tests. So if you look at this slide, what you actually see here is that adding positive results, as we've said, increases the probability of being infected more than adding negative results decreases the probability of being infected. And that was what we did in the previous page. So this is just a sort of semi-graphical mathematical illustration of why there is a difference. So I thought I'd put in a few more fanciful ideas before I finish this presentation. A lot of people are now repurposing their research, especially in engineering, computer science, and trying to see if they can adapt it to dealing with COVID virus. So this is an idea that came out of MIT a while ago, and what they had been doing was they'd been looking at Doppler shift on reflected Wi-Fi signals from the beating of the heart. So they're trying to repurpose this, I believe, to look at the Doppler, micro Doppler shift due to breathing. And I think the idea is that the breathing is affected when you're suffering from the symptoms of COVID-19. And can you identify that difference in the breathing from other types of breathing to say that someone has the virus? I mean, you might ask the question, if someone's standing in front of you, why not put a stethoscope and just listen to the breathing rather than using Wi-Fi? But I suppose this is something where people are walking past Wi-Fi signals and you're just automatically looking for irregularities in breathing, where presumably again you've trained some machine learning algorithm to recognize these differences. So originally this was an MIT research to the use of Wi-Fi to measure the beating of the human heart. So let's just see what that original research was like. It was basically this: imagine you have someone who is, say it's a hostage situation, they're in another room, you've got Wi-Fi all around you, and the Wi-Fi signals are hitting both the hostage and the hostage taker, and there'll be a beating of the heart, and that heart will produce a micro Doppler shift in the return frequency, assuming the person is standing still, there's no other frequency shift. And in theory you can receive that with an antenna and then analyze and extract the heartbeat, and you could look at the emotion of the person and to see what sort of state they're in if you're negotiating with the hostage taker. So that's allegedly being repurposed to deal with COVID. Another idea that came out of EPFL in Switzerland is that, according to the World Health Organization, 67.7% of people who have the virus present with a dry cough. So this is AI machine learning analysis of cough audio, and it's called cough vid. And what it does is you train an algorithm to recognize again the type of cough that you have when you have coronavirus. And having trained that algorithm, you simply cough into your mobile, and you probably get a message saying that perhaps you should see a doctor if it thinks that the cough indicates that you might have coronavirus. So another idea that's been developed at EPFL in Switzerland is ProCam. And the idea here is that you have a thermal camera for fever detection, and it could be in airports or restaurants. There's nothing new about having a camera to look at whether you've got a fever or not. But the difference with this particular camera that they've developed is that its accuracy is very sensitive, so it must be better than plus or minus 0.5 degrees centigrade. And what these cameras do, so you're just walking past a camera in an airport or you're in a restaurant, and it will identify you if you've got a possible fever, and then it will track and trace you using traditional cameras as you walk through a part of the airport or leave the restaurant, and eventually it will contact you and your contacts. So that's the clever thing about it. It's the track and trace after having detected whether you've got a possible fever. Of course, there are privacy issues here as well, which have to be considered. Okay, we've reached the conclusions section. First conclusion is that accurate testing for the virus is extremely important, not just to know how many people are infected at any one time, but to be able to estimate instantaneous values of, say, R0 or case fatality rate, or if you're easing lockdown, you have to know how many people are currently infected, because do you increase the lockdown or do you ease it even more? So very important. The Lancet editorial said on the 14th of May regarding the UK government, quote, especially shambolic has been its approach to testing and contact tracing. So these aren't my words. This is in the Lancet editorial. The estimation of the prior prevalence of the disease is really important, because unless you know that, you can't work out the probability of false positives and false negatives. So someone might test negative, and you might not know that the false negative had a 11% or 15% chance of existing, release them back into the community and they infect others. The maths is very similar to many engineering applications, and it's equivalent to first year undergraduate in science or engineering. In fact, the maths is no different than probably final year at school. PCR specificity is much higher than sensitivity, so false negatives is much more of a problem. That means that the PCR test is very good at confirming that it's a disease. If you test positive, then you can say pretty confidently you've probably got the disease. If you test negative, then there could be 11% or higher of a false negative, and that's quite worrying. A symptomatic infection is not covered by symptom-based screening, and also given that you might not exhibit symptoms up until 4 days or 5 days, if you test during those 4 days, as we saw earlier, then false negatives can occur with very high probability, depending on the prevalence of the disease. We also said that many engineering applications are being repurposed and used to now model virus spread. Examples of those were in sensor networks and communication networks. And what we can certainly do is consider the sensor to be an individual who's either got the virus or not got the virus, say on or off. We can look at clustered stochastic geometry where we model hotspots, or we can thin a 2D random process whereby we remove sensors because they've either, or people because they've either become immune due to vaccination or having recovered from the virus. So there's a lot of potential to reposition existing research to deal with modeling the spread of this virus. And finally, it's only 5 months since the virus appeared on the planet, so there's not enough hard data yet. In months to come, we'll have a lot more data, and we'll be a lot more knowledgeable about how this virus is behaving. Okay, thank you so much for listening, and please keep safe, and sorry for any mistakes. Oh, and finally, don't inject yourself with bleach. It's very dangerous and very silly.